Monday, I believe in this class we were able to start talking about the phantoms model and running a full hypothesis test. So we're going to practice that one more time today, and then you can work on your assignment. A couple things first I want to remind you of is that you know that your null hypothesis is always an equal to. Always an equal to. Even if they say something like, they will be happy if they have 8% or less. Okay? They will have met their goal if they have 8% or less. Hypothesis value is always equal to. Okay? This alternative value is going to be a not equal to, or a less than, or a greater than. That's for the alternative. Now, the way I want you to think of the alternative is this. What kind of sample gives you the ability to reject the null? So if you end up rejecting the null, is it because you got a value way too high, or you got a value way too low, or you got either one of them? Okay? All right. So that's what you're thinking of. Now, the next thing, which we already did do on Thursday, but here this is, the test statistic is your z-score. And you can see that your z-score is the sample that you get, and you compare that to the proportion that is claimed, and then on the bottom is that standard deviation of the sampling distribution. Now here's a common mistake that I want you to watch for, okay? Frequently we see this little p-hat here, and then we get sucked into putting the p-hat value right there for the standard deviation, and that's a no. You will have a true p that is your hypothesized p-value. You will have a hypothesized p-value, so make sure you put that hypothesized p-value here, not the p-hat. And likewise, when you do the large enough, that is also the n times p, the hypothesized value that goes in there. Okay, so let's do number one completely together. Here we go. A company with a fleet of 1,500 cars found that the emission systems of 17 of those 53 randomly selected cars from their fleet failed to meet pollution control guidelines. Okay. So what they're doing is taking a sample and then inferring about the proportion that failed to meet guidelines in the entire fleet. What does that do if you can do one sample instead of testing the entire fleet? That's saving a whole lot of money, for one. It's also sometimes, you're going to be inaccurate if you're trying to do everything because there's so many and so forth. So sometimes there's inaccuracies when you try to get a whole census. Okay, so here we go. If a significant number of vehicles are found to be out of compliance, then the whole fleet will have to be inspected and brought up to current regulations. So that would be incredibly expensive for the company. Is there strong evidence that more than 20% of the fleet might be out of compliance? So that's what you're going to be checking for. Use a 1% level of significance. Let me explain that real quick before we go on. This means that the alpha you are going to be checking against is 0.01. So if you get a probability of getting your sample or something more extreme that is lower than this alpha, then that's considered statistically significant. So they are defining for you what type of probability is going to be considered significant. If they don't tell you this level of significance, you go with 5% as kind of the standard. All right, so if you're not exactly sure what I'm saying there, just hold tight. You'll see how that plugs into when we do the problem, which we will do with a complete hypothesis testing template. So turn there and let's do problem number one. Okay, so the proportions that you are getting, what is the proportion that you are going to be inferring about? The proportion of what? Okay, good. Proportion of the entire fleet. This has to be about the whole population. The proportion of the entire fleet that I guess that fail pollution guidelines. Fail to meet pollution guidelines. Sorry, I left that out. Now, this morning during second period, I made a big old boo-boo, and I used the word failed here. The proportion of the fleet that failed, past tense. That is a big no-no, because past tense can absolutely be determined. You don't need to infer anything about past results. You could get that answer. You are taking a current answer and making an inference about the current failing proportion of cars. Okay. Current proportion. So make sure that it's always current tense, not past. All right, so what's our hypothesis statement? Our null hypothesis is going to be that P, what? Always equals, so P equals what? No, not 0.01, that's our alpha for later. 20%. So 0.2, 20, 0.20, whatever. Because that is kind of like that stick in the sand where if you go way above that, if we end up rejecting this, then the company is in hot water because they're going to be having a lot of expense to fix the entire fleet. So what type of, if we get a sample that is way what will it cause us to reject the null? If we get a sample that is significantly greater than 20%, then that's going to cause us to reject the null. If it's significantly less, I don't care, that's actually good. If it's significantly greater. And so then these assumptions are our same old assumptions that you always do. So I want you to put those down right now while I write all those down. So go. That number 1,500 that they tell you at the beginning of the problem, what is that? That is the size of the population that you are taking one sample and then inferring to. So you didn't have to put this right here, but just keep in mind that because they told you the size of the population, you actually could confirm all of these things for sure. I have nothing that is extra here. You should have every single thing that I have here. Notice that this N times P is this 0.2, and N times the 1 minus P is the 0.8, and of course your N is 53. That's the size of the sample. Okay, what is the name of the formula, or name of the test, sorry, that we are doing? It's a 1 proportion Z test. So we now have two things that we know what to call them, 1 proportion Z interval and a 1 proportion Z test. Okay. But we'll get to that. That's going to be called a 1 sample. It's actually probably going to be a T test. Anyway, so see, that's a whole nother ball of wax. That's why we do proportions separately. So I'll walk you through that when we get there. Okay. confidence interval, we're not doing the confidence interval, but we are going to be doing the test statistic. Now you remember that the test statistic is the z-score, and you don't have to write this, but I'm just going to put out to the side to remind you that the z-score is your sample compared to the claim, the hypothesized p, over the standard deviation of that sampling distribution. Okay, so keep in mind that's what you're going to be doing. So let's make sure we have those values. What is our p hat in this problem? It's that 17 over 53. That's the sample results that you got, and that is 0.32. Of course, p is your 0.20, but let's do standard deviation of the sampling distribution. How do you get that for proportions? What? Yes, use the true p. That's the square root of, make sure you use the true p of 0.2. Okay, and so that number is 0.0549. All right, so we're ready to do this, get this z-score. Please do not just write 0.32 minus 0.20 over 0.0549. You need to put z equals. You need to identify what you are calculating. You can't ever just put random things there and let somebody, assume that somebody knows what you're calculating. No. This comes out to be 2.19. So, at this point, your brain should start kind of having a thought about this sample. Based on a z-score being over 2 standard deviations out, what are you kind of thinking is happening with this sample? It's kind of far out there. So I'm a little concerned, all right? But I will tell you, you do not have the ability to reject the hypothesis with z-score. It has to be done with the p-value. This is the thing that allows you to reject, comparing that to alpha, which the alpha that was given to us was 0.01, not 0.05, but 0.01. Okay, so we need to figure out that p-value. So before we do that, I want to make sure you understand what p-value is. And here it is. I've drawn this picture. Here is your null hypothesis. This is the assumed or the claimed p, true p. What the p-value is the probability that you get this sample you got or something more extreme. So again, p-value is the probability of getting that particular sample you got or something more extreme if this null is true. So if you get something way out here that is basically maybe a 0% chance that you would have gotten that if the null hypothesis is true, then if you get something way out here and the p-value is basically 0 because this was so unlikely, then you go, hey, null hypothesis, there is no way you could be true. You are totally in the wrong place, and this curve is really all shifted up this direction. Because I got a sample, and it shouldn't be that rare. So null hypothesis, you are way wrong. You are something greater in this case. Yes? Correct. And that play, like making an incorrect decision, such as failing to reject when you should have rejected or rejecting and you shouldn't have, that comes into actually the next chapter when we discuss what are the consequences if you got a weird sample and you rejected and weren't supposed to, or the other way around. So that is a topic to address. One last thing I wanted to say. If this was a problem where we were talking about something being way too small, of course you would be interested in p-hats down here, and then the area you would be talking about is something from here, or something more extreme would be out this direction. Okay. So here we are. We've got this p-hat, how do I find this p-value for our sample? Good. So we are going to norm CDF from R 2.19 out to 99 to get the p-value of 0.0143. So there's a 1.43% chance that we would have gotten that sample if the null hypothesis is true, which to me doesn't seem very likely, but they gave us a very low alpha. So now, put a sign in between these two things, less than or greater than. Yes, the p-value is greater than alpha. And the rule is, if the p-value is low, the null has to go. Since this p-value is not lower than alpha, does the null hypothesis go? No. So then what we do is we say that we do not reject the null. And the way you word that is you fail to reject the null because your p-value was not unusual enough. Your sample was not unusual enough to reject the null. Even though it's more than 2 standard deviations, and the reason is because whoever was setting the rules for this test said, I need you to be really, really sure because this is going to be a major expense, so I'm going to put an alpha that's really, really small so that if you get something out there, then it's pretty dang sure that they are way out of compliance. Okay? All right. So now, let's talk about stating the conclusion. I kind of have an outline of what I want you to include, so here it is. The first thing I want you to include is basically restating the p-value information and your decision. Okay, then you need to go back up and look at your context, include context. And then the final thing that you are going to include in your conclusion is make sure, go back and look, and make sure that you answer the question that it specifically asks. Don't go rambling off all this stuff without actually answering the question that it specifically asks. Okay? So let's do this. You're basically going to restate this and this. So you say, since the p-value is greater than alpha, I fail to reject that. So don't put just the HO right here. Now you put in context. So I fail to reject that. And you know where you find context? Up here. So this is where you're going to get your context from. I fail to reject that the proportion of the entire fleet that fails the pollution guidelines equals 0.20. Okay, so I fail to reject that the proportion of the fleet that fails to meet the pollution guidelines is 20%. So I do not have the ability to reject that. Okay, now we answer a specific question. This is always a statement about the alternative. Statement about the alternative. And see, and this thing says, right here is the specific question. Is there strong evidence that more than 20% of the fleet might be out of compliance? Okay, see, so it is a question about the alternative. This question is always going to be a statement. So do I have evidence that more than 20% is out of compliance? No. So you word that and you say, therefore, there is not strong of the fleet is out of compliance. Okay, so that is the formula that you follow for a full and thorough conclusion. And this whole page is the formula you follow for a full and complete test. Hey, let me tell you something. It's a big deal to make an inference about the entire population from one sample. So that's why all of this is required. Because you're going to be making an inference about the entire fleet from one sample. So by golly, you better have every aspect of it covered and quote unquote, like defined for the person. Okay? So now I want you guys, you got a full 30 minutes to work on your problems. And if you work on them, then good during this class, you just have to do 4 of those instead of 6.